Welcome to the second lecture video in our Class 23 series of lecture videos. We ended the first one looking at bromination of alkenes. We will continue our study of bromination of alkenes under different conditions. Instead of having this bromination take place in a polar aprotic solvent like dichloromethane, what happens when we add our diatomic bromine to an alkene in water or some other polar protic alcohol solvent? Well, then what happens is we form our cyclopropylbromonium cation. However, it's water or that other polar protic alcohol solvent that opens up that ring. So in the case of this particular alkene and water, we have, our bromine, we could add the bromine, form that cyclopropylbromonium cation from the top face, and then if water comes in and opens it from the back face, we get this trans relative orientation between our hydroxyl group, which is basically what happens after you deprotonate the water molecule that added in, and the bromine group. Alternatively, we could have added or formed our cyclopropylbromonium cation from the back face of this alkene, and then water will come into our more sterically hindered tertiary carbon and open that up. And again, we have a trans orientation, relative orientation of our hydroxyl group and bromine. These are related as non-superimposable mirror images, so they are enantiomers. We would expect a one-to-one distribution of them. It's a little unusual that I am saying that the water is opening up our cyclopropylbromonium cation intermediate in an SN2-like fashion, attacking the most hindered carbon. It's somewhat like something we've seen before in that we've looked at epoxide ring openings under acidic conditions, and you don't get racemization, right? It looks like it goes through an SN2-like transition state. It could be that the cyclopropylbromonium cation opens up first, but shields the face from which it had been formed initially. So the nucleophile has to approach the p orbital from the other side. So what am I talking about? Here I am discussing how this bromine forms the cyclopropylbromonium cation from the top face, and this is what I talked about when I said, oh, water is reacting, doing a backside attack like an SN2 reaction to open up that ring, and we deprotonate water using another molecule of water to seal the proton, and we get that trans orientation. You could do the same idea from the bottom face, and you would get the enantiomer. The confusing part is how can you suggest that we could do an SN2 reaction with our weak water nucleophile attacking that tertiary carbon to open up the ring? And like I said, it could very much be a case like the epoxide ring opening, where this actually opens up first, but the bromine shields the top face of that p orbital, and the water has to come in from the back face. But definitely an unusual aspect of this chemistry, and one that you will be asked to keep straight as you encounter problems in your exam material. Again, we could do these brominations not only in water, but we could do them in an alcohol solvent. Here we have methanol. Methanol opens up our cyclopropylbromonium cation intermediate, and in this particular case where we've got trans 2-butene, we end up with these enantiomers. So try practicing an arrow pushing mechanism to form both products. It's always a useful exercise. Chlorination also works following a similar scheme. So you can think about forming cyclopropylchloronium cation intermediate and opening it up with water. Other reagents could be used, like we have this bromochloride or chlorobromide, depending on which way you like to name your heterodiatomic halogens. Again, you would form a cyclopropyl bromonium cation and kick out a chloride anion because the chlorine is more electronegative, but that chloride anion could open up your cyclopropyl bromonium cation. And here we have bromine bonded to a nitrile group or a cyano group. And we have this cyanide opening up our cyclopropyl bromonium cation. All right, well, I've said that enough. Obviously, I'm tiring of it. You could get this, and it's an enantiomer. How are these products used? Well, I mean, if you added sodium hydride to this molecule, you could form an epoxide. We've seen several uses for epoxides as synthons. Definitely, you could use them to form carbon-carbon bonds with Grignards. So there are uses for the products of these reactions. That pretty much finishes this video. Good luck with the question that follows, and I'll see you for the next video.